Well, hello, chemistry students. This is part 3. Finally, it's going to be done of the Unit 2 Matter and Measurements test and review questions. Yes, even you can get a good score on this test if you go through and practice this and come to the study sessions that your teachers are having for you. So, I'm assuming we've already gone over part 1 and part 2 of the video. So, without any further ado, let's get going. So to begin with, how is a chemical change different from a physical change? Well, with a chemical change, you are getting new substances formed, new chemicals, or if you like, new chemicals formed. You're getting something new, like wood is changing into, here's an example for chemical. Wood plus oxygen, oxidizing, plus heat, like fire, can change it into, I guess it's going to be CO2. It's going to change it into some water. I'm going off the page. Whoa, I'm going off the page. CO2, water. You'll get some heat, and you'll get some light, etc. Okay, it's totally changing. So now, how is a chemical change then? How is a physical change different? Well, a physical change, it's still going to be the same chemical. Ice, water, and steam are all H2O. They're just solid, liquid, and gas form of it. Number 4. Do as a, pardon me. So I made a mistake on it. Give me a break here. Does a compound, that's supposed to be does, D-O-A, does a compound have the same chemical properties as the elements that make it up? Well, let's say compound. Well, we had one up here. Well, let's kind of look back to here. So we have, in this problem, we had gaseous, burnable hydrogen. We had gaseous oxygen that is needed for burning, and then we had the compound that those two formed into being very stable and a liquid. So very different chemical characteristics over here. Now let's come back. I'm going to give you my favorite example. Okay, so compound, table salt, NaCl, sodium chloride. I'm going to zoom in now. If you don't like it, well then that's a bummer. Now, sodium chloride is table salt. There's lots of different salts. Salt is technically a metal bonded to a non-metal, but when we say salt, we're usually thinking table salt. Okay. Now, sodium. Table salt is stable. We do need a little bit of it for. Life depends on this. Life needs this. Now, like with anything, you can get too much, it can kill you. You drink too much water at one time, and it'll dilute your system out because it'll dilute the salt out of your system, you'll die. So, this is very stable. We have to have salt in proper amounts. However, if we were to break this apart into sodium metal, which is a shiny silver metal, and if you were to put this shiny silver metal in, and let me back up here. Salt is a white substance. It's a crystal. Zoom in here, and it's brittle. We're not even going to get into taste and stuff. So it's a white crystalline brittle material. You know salt. Now, if we go through a process, which you can do, and I'm not going to tell you because you'll go do it and probably burn your house down, you can get sodium metal. Sodium metal is a silverish metal. It's very low density. So now look at here. It becomes a silvery metal. It's different from this. So it's a silver metal. And it's soft and squishy. You could probably push it and squeeze. You might need to. It's soft. You will also get chlorine gas per chlorine, which it'll exist as chlorine gas. Now chlorine is going to be yellowish green. It's going to be a gas. And if you inhale it, it will mix with water in your body and change into a terrible chemical in your lungs called hydrochloric acid. So that's going to be bad. So chlorine is toxic. Now, the reason we put chlorine in water in low amounts is to kill germs because it's toxic. So you've got sodium metal. In fact, you put sodium, it's so reactive. I mean, it's a soft silver metal. You put it, bang, it blows up. Chlorine gas. You inhale it. Oh, I dropped my pen. So it's going to be, okay, I got to find another one. I'm kind of in a panic here. There we go, got it. But you combine them together and you get a chemical we cannot live. It's like the greatest love story ever told. Greater than Romeo and Juliet. Okay, moving on. Over here, this problem. The problem is asking, how many electrons are in one atom of gold? Well, if it has not done any reacting, the protons that the atomic number tells us will attract an electron. So how many electrons in one atom of gold? There will also be 79 electrons until chemical bonding occurs. And let's see, coming on down to the next one here, number 8. Explain why the nucleus of an atom is relatively heavy. Well, in the nucleus of the atom you have protons with the plus charge and neutrons with no charge. So they're jammed in there pretty close, really close in fact. So you get, these particles have weight. They have, each has a weight of one atomic mass unit. Now, if you come way out here to the shell and look at an electron, there it is, there's the electron way out here in the shell. Okay, now electrons have they're almost a 2,000th the weight of a proton. It would take almost 2,000 of these to equal one of those. So they do have some mass, but they're extremely tiny. So these are really close together too. They're squished in together, so the nucleus, even though it's very small, it's pretty heavy. You wouldn't believe the density of the nucleus of an atom. It is so dense, it's like as dense as a neutron star, which is like if you had a teaspoon of nuclei, of atoms, it would weigh millions of pounds. I'm not kidding you. Nuclei are dense. Anyway, continuing on. Number 10. Compare the size of an atom's nucleus to its shell. Well, okay, I can't quite do it very good. Let's say here is the football stadium at Buchanan High School, Veterans Memorial Stadium. Okay, so that would be like the shell, the stadium, and a grain of sand right in the middle of the track would be like the nucleus. The shell would be the stadium. Nuclei are extremely tiny. The shell goes out really, really far. It's unbelievably big. Moving down to number 14. So we went over this stuff, I think, in part 1. Isotopes, to remind you, are just they're just different. They're elements that might be heavier or lighter. In this diagram here, we had helium-3, which means it's helium that was missing the normal neutron that it has, so it only has a mass of 3. Most helium atoms have 2 neutrons in them. Oh, wait, let me back up. This one is missing a neutron. I might have said that wrong a moment ago. So this one's missing a neutron. It's slightly lighter, has a mass of 3. This one has the usual 2 neutrons, so it has the usual mass of 4. So anyway, isotopes may have, this is kind of getting us ready for the next unit, isotopes of elements can have the same number of protons, okay, but different number of neutrons. So in this one right here, we can add in, if we want to add in a whole bunch of neutrons, this is still helium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've just drawn helium-10. That won't exist in nature. It's too unstable. But it's still helium because it has 2 protons. Okay. Now, if we come over to this helium, and if we were to throw in another proton, now we've got 3 protons. This is no longer helium. It is now lithium, because lithium is the element that has 3 protons. So, an isotope is just an element that has extra or fewer neutrons. Protons can't change. You change the protons, it becomes a new element. Let's turn it over. Here we go. So we're on the top over here, number 16. Weight is a measure of the pull of gravity. If you're on a very massive world like Jupiter, it has much more mass. Its mass will pull with a greater amount of force, and that's gravity. Mass is a measure of the number of atoms in a sample or in something, okay? So an astronaut goes to the moon, they still have the same number of atoms, their mass doesn't change, but the moon is so much smaller than the Earth in mass that it can't pull on the Earth as strongly. All right, continuing on now. We have two planets here. Planet Obi-Wan, the force is strong with this one. Okay, I couldn't resist it. And the other planet, Jar Jar. Okay, now Jar, get out of here. Out of there. Okay, where was I? Okay, so what do we got to do? What's the astronaut's weight on each planet? I've given you a hint. Okay, now look it. If you're really paying attention, you might have noticed that I said weight is the mass times the gravity factor. But I actually, and I gave you, I didn't give you a mass right there. Sorry, just work with me. So what we're going to do is on planet Obi-Wan, we're going to take the weight, which, sorry about that, we're going to multiply the weight by the gravity factor, which we said was 2.3. And when you get that, you're going to get some bigger number. I don't know. I'm going to guesstimate that it's going to be, probably looking at this. This is almost 200. This is, okay, it's going to be about 400. Okay? I'll let you actually do the math on that, okay? So, okay, it'll be about 400 over here. Oh, it's 414. I can't stand it. Okay, now on planet Jar Jar, Mushin Bombad planet here. Stop it, Jar Jar. Quit it. Get out of here, okay? Out of there. Okay, Jar Jar is, again, same weight. Okay, mass. Sorry, I should have said this was kilograms. Okay, 180 is how much there would have been on Earth. But then on Jar Jar, the planet is 0.4. So we're going to multiply that by 0.4. And I think we end up with a little bit less than 100, because 180, and when we multiply by 0.4, that's going to be less than half of that, and it comes out to be 72. And I guess this would have had to be pounds, and this would be pounds. Sorry that Mr. Lake, the physics teacher, will be mad at me for getting pounds mixed up with mass. But anyway, there we go. But the idea is, if you're on a world, on a planet, on a place, that has more mass, you're going to weigh more. In fact, here's a factoid for you. The Earth is, I'm exaggerating here, the Earth is shaped like this. And if you stand here on the North Pole, you are actually going to have a greater weight here because you're closer to the Earth's center of weight, so the gravity factor is bigger. If you stand over here on the equator, you're a greater distance away, you're going to have a lesser weight than you would over here. When we send ships from like the equatorial regions over towards the poles, they have to do a calculation because the weight will actually change. But anyway, we don't care about that. We want to continue on. If the box above, the one that we figured out had this volume before, let's see, okay, blah, 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 blah. Oh, what's the box's volume? Now, we've got this really cool equation triangle. We're looking for volume. You cover up the volume on an equation triangle, and it is going to be mass divided by density. So, volume equals mass over density. Now, be careful. It's real easy to mix that up. Please, please, please. In fact, I insist. We all insist. Start with the equation you need. Volume is mass divided by density. Let me make sure I did that right. Yeah, okay, boy, I'm even double checking. So we're going to put in 430 grams is our mass. We're going to divide it by the density. Wait a minute. Wait a minute. Did I goof up? No, we're looking for volume. Okay. We got this mass. Excellent. We got this volume, 1,005. I see I'm sitting there. I'm kind of tired right now, so I'm. Okay. So wait a minute. We're looking for the box's volume. Volume is mass. Okay, I am really tired. Yeah. So, we're 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,005. 1,0 Oh, wait a minute. Okay, sorry everybody. Let me back up. This was a typo I did. Okay, we already know the volume. This is supposed to be density. Sorry, I kept getting. This was not to be. I did not mean to be trickier. We're looking for density there. Sorry about that. Because if you, those of you who said it's 1,541, yes, we're looking for density. Density is mass divided by volume. Sorry, I was kind of quiet there. My brain was going, wait a minute, something does not compute. The mass is 430 grams. Okay, so I knew what I was doing, but I just didn't have it set up right. We got the volume of 1541.8. Okay, and so when we do this out, we're going to end up with a pretty small number here because we've got 430 divided by 1,500. Let me double check because I have made a mistake on previous ones. Okay, 430 grams, good. This is the volume we calculated before in centimeters cubed. So about 400 divided by about 1,500. I mean, see, 4 goes into 15 like, oh man, that's going to be like, oh man, like what, 4.5 or something like that? I don't know. I think I wrote the calculation down. Let's check this out. 430 divided by 1541.8. And yeah, a number like, and we're supposed to round to one decimal place. So 0.27 will round to 0.3 if we're going to one decimal place. And that's going to be grams per centimeter cubed. Sorry about it. That was a typo on there. That was supposed to be density on there. Okay, moving right along because now I'm partially embarrassed here. Let's go. Now, in this problem over here before, we calculated, what was it? Calculate their volumes. Okay, now this time, we're calculating their masses. And when we're working with mass, here's the equation triangle. Okay, mass is density times volume. So I'm going to put here, now for each of these, we're going to have mass is density times volume. And you're going to, now I'm not going to actually do the math on this. You can work that out. You have to work that out. But the density for aluminum is 2.7 grams per centimeter cubed. And then we're going to multiply that by 5 centimeters cubed. Okay, and that will give you an answer. This is for aluminum. Now we're going to do iron. Mass is density times volume. And so we're going to put in there the density for iron is, I'm going to put Fe, that's the symbol for iron. I'll put Al over there, just so we know. Let me zoom in here, you're probably watching. Okay, so let's see, we've got 7.9 grams per centimeter cubed. We're going to multiply that by the volume. Again, the volume on all of these samples is 5 centimeters cubed. And that's going to equal, well, we got 5 times almost 8. So 5 times 8 is like, yeah, almost 40. Over here, look at here, guesstimate. We've got 5 times almost 3. Okay, so this is about 15. This is about 40. And then for gold, okay, I'm going to have to do gold a little bit lower. Mass is equal to density times volume. This is for Au. That's the symbol for gold. And, oh, sorry about that. Let's scoot that over. And the density of gold is a whopping 19.3 grams per cubic centimeter. So that's pretty dense. That's a pretty good density there. In fact, so what that means, just to refresh your memory, that means if you had a cubic centimeter of gold this size, it would weigh 19.3 grams. Over here, the iron, the same amount, volume of iron would only weigh 7.9. And if you had a cubic centimeter of aluminum, it would only weigh 2.7 grams for every cubic centimeter. So density kind of gives us a little indication of how many atoms are packed into that area. So we've got 19.3, and we're timesing it by the volume, which is 5 centimeters cubed. Those cancel out. Now this is almost 20. 20 times 5 is like close to 100. So to end this question, list them in increasing mass. This was almost 100. So that's going to be the heaviest, Au. The medium, the middle weight one was going to be the iron, so I'm going to put Fe. And then the lightest one was aluminum. And let me make sure, list them in increasing mass. So more and more and more. So we have, that's the increasing mass. Again, you can do the math, but again, about 15, about 40, and about 100. And those answers will all be, because we were looking for mass, in grams. Forgive me for not putting those in. Oh, over there. I'm sorry, didn't mean to cut you off there. Take a look there. All right, number 24. You have, we're looking for mass. Okay, so we just did mass. Mass is density times volume. The density of this frozen lava, 3.2 grams per cubic centimeter. We're going to multiply that by 219 centimeters cubed. Okay, I'm going to move on. Okay, this is about 200. This is about 3. 200 times 3 is like about 600. So this will be a little bit bigger than 600. You do the math yourself. Number 26A. All right, how many centimeters in 100 meters? On your test, you're going to have a set of, in fact, it's going to be those very calculations right there. So you need to refer to that. How many centimeters in 600 meters? You always start with what's given, 600 meters. In fact, I'm just going to turn that into a fraction just because doing conversions, also known as dimensional analysis, is just multiplying a series of fractions. And really, those fractions you're multiplying, they really just equal 1, but it converts the units they're in. So let's see, if we take a look, we want to go to centimeters. So on the front page over there, it gives us a conversion that says there's 100 centimeters in a meter. So since I want to get rid of meters here and I want to go to centimeters, and I do have that really nice conversion there, we know that 100 centimeters are in 1 meter. And then that's going to cancel out like that. And then you can do the math. That's going to be like 600 times 100. Wow, that's going to be like 6 followed by 4 zeros. Now, how many miles is this? Okay, so now what we got to do is we got to convert it into miles. Well, I'm just going to go back on this one. I'm going to start again with 600 meters. If you don't like that, well, bummer. Okay, now I'm going to put that over 1 because it's just a fraction. Now, meters to miles. Now, do we have on the front over here, we have kilometers to miles. Oh, look, we have meters to kilometers here. So what we're going to do is we're going to have to convert this into kilometers, and then we're going to convert the kilometers into miles using those conversion factors there. So let's see, according to this conversion factor, we want to have meters turned into kilometers, and I think if I remember right, there's 1,000 meters in 1 kilometer. Yes. And now 1 mile is 1.61 kilometers. Oh, I was off there. There you go. Looking at this one right there. So let's see, where are we? I got lost. There we go. So now we want to convert, now we want to get rid of the kilometers and we want it to be miles. And it said 1.61 kilometers is 1 mile. So now the meters cancel out, the kilometers cancel out. And let's see, you know what? I'm just going to show you a trick we're going to show you. We're just going to cancel that 0 with that 0 and that 0 with that 0. So now 6 divided by 10 is like 0.6. So we're going to divide that by 1.1. So anyway, you can get the math. I think it works out to something like 0.375 miles, okay? So you could work that out yourself, okay? That's how you set it up. And if you don't like what I did, canceling the zeros and just do 600 divide. Now, on your now that's a good point here. On your calculators, with your scientific calculators, they're really cool to use. Or if I can find the clear button, you just have to put 600. You're gonna clear 600. Now we got to divide by 1,000. Divide by 1,000. Oh, one more there to make it 1,000. And then we got to divide again by 1.61 divided by 1.61. Okay, so that answer is going to pop out to be like 0.37. And I don't know, if we said round this off to 1 decimal place, we'd round that to 0.4 if we're going to 1 decimal place, and that's going to be miles. Scientific calculators are kind of cool to use. All right, for number 28, let's see, what do we got here? Convert 60 grams into kilograms. Well, okay, 60 grams. Now we have to go to kilograms. I think we have a direct conversion right over here. Where are we? Grams to kilograms. Oh, we didn't put the grams to kilograms on there. Grams to, well, 1,000, well, 1,000 grams is, oh, look at there. We didn't put that on there for you. That would have been kind of a pain. Grams to kilograms, huh? We got kilograms to pounds on there. So let's see. So we're gonna have to go to an intermediate because we got to convert this first into. Let's see, what do we got here that has grams and kilograms? Kilograms. You know what? On this one, sorry everybody, I'm just gonna put it here. 1,000 grams equals 1 kilogram. So that was probably when we left off. So the prefix kilo just means 1,000 grams there. So I guess I left that one off. I'm not trying to be mean to you. So with that conversion factor, I'm going to put that over 1. 1,000 grams is 1 kilogram. So we'll get that set up. So when we go to do this, we're going to enter 60 divided by 1,000. If we want to make it easier, we can cancel that 0 and that one, and it becomes 6 divided by 100. The answer is going to be like 0.006. So this is going longer than I meant to. Sorry about that. Yeah, this would be 0.006 kilograms. And now we want to convert this into pounds. So 0.006 kilograms. We do have thank goodness, we have a direct conversion over here. We got kilograms to pounds. 1 kilogram is 2.2 pounds. Oh, thank goodness. So we want to get the kilograms converted to pounds. LBS will be that. And I believe, I better be careful. 2.2 pounds is 1 kilogram. 1 kilogram is 2.2 pounds. So now you just multiply that out. So 0.006 times 2.2. Oh, did I get this? Where are we? We're right there. Sorry, everybody. And you should have around 0.132, which that kind of makes sense because that's about twice what that is, okay? So anyway, almost done. In fact, I think we're on the last one right here. Okay, if you are, let's see, 51 inches tall, how much centimeters is that? Well, we're going to start with 51 inches. On the conversion factor up here, we have, let's see, where is it? 1 inch is 2.54 centimeters. So I'm going to make that a fraction. We want to get inches canceled out, and we want it to be centimeters. And we said 1 inch was 2.54 centimeters. That was from the front. Oh, I did it again. I didn't get this centered. Sorry about that, everybody. So we put what's given. I just put it over 1, so it's kind of like a fraction. Sometimes that's kind of helpful. Then we're multiplying that by 1 inch in the denominator is 2.54 centimeters there. We're going to cancel those out. And we're going to end up with, that should be 129.54 centimeters. Okay, now, how tall is that in millimeters? Now, this is going to be a two-step conversion because with the conversions we've given you 1 meter is 100 centimeters, which will be the next one. We'll convert the centimeters into meters, and then we have right here 1 meter is 1,000 millimeters. So this is kind of be a little bit long way to do it, but it'll work. So we're going to start with what's given, 129.54 centimeters. That was the answer to our previous problem. Okay, so now I'm going to just put that over 1. And we're going to multiply that by our first conversion factor. We want to convert the centimeters. Let's see, we're going to convert the centimeters into meters. And so on our conversion factor, we want centimeters into meters. And it says 100 centimeters is 1 meter. That'll cancel those. Then the other conversion factor we had on the front. I know these can be kind of a pain. They're tougher problems, so you got to kind of ferret them out, if that's the right use of that term. So let's see. We want to get rid of meters, and we want millimeters. And the conversion factor said that 1 meter is 1,000 millimeters. Meters will cancel out. So when you go to multiply this all out, what we're going to end up doing is we're going to be taking this in your calculator, 129.54 divided by 100 times 1,000. And that's going to end up coming out to, or if you're smart and looking ahead, cancel out those 2 zeros with that 2 zeros, and it really becomes 129.54 times 10, which equals 1,295.4 millimeters. Okay, I'm done. I'm tired. Hope this has helped you out. Goodbye, everybody.